We continue. I go give you now a lot of examples on what we did with the techniques that we discussed in this course. If you have the blood vessels, you want also to detect things outside the blood vessels. So we raised the question, can we remove the blood vessels? And yes, of course, you can remove the blood vessels. You know them, and then you can threshold, and you can put black spots or white spots in the pixels that you have removed. But that's not nice. It would be better if you fill up the places that you have removed the vessels with the same texture. Well, you can do that. It's a fourth-order polynomial, let's say, extrapolation technique. And you can see what is the neighboring texture and what is the texture on the place next door. You know what is the texture because we have all these Gaussian derivatives to very high order. So we know the Taylor expansion to very high order of describing the little structure of my background right there. Well, that structure you can copy and say, okay, then we put that in the vessel. That's called a filling in technique, and in computer vision it's called in-painting. And you see the results of in-painting here. If you remove the vessels, it's much easier, and unfortunately the screen is not so contrast-rich, but you see a microaneurysm here. It's far easier detected without the blood vessels than with the blood vessels. So if you can remove them, doctors do this. They have a chest ray image and say, well, think away the ribs and then look for the tumors. Well, that think away you do in your brain. It's actually a little bit the same as this. So this filling in is quite an important thing in painting. We did de-blurring techniques. This was progressive blind deconvolution. So if your camera is not really sharp, we have seen that we have different ways to de-blur. And now what you can see is every cone and rod here, or receptive field, the ganglion cells, they have a fiber, or 1 million fibers going to the optic disc. And now finally you can see the fibers. So there's an incredible range of fibers running over your retina. You normally don't see them, but with the de-blurring you can see them. And some people have, of course, damage to the neuron layer. Well, we have seen in extenso the optical measurements from the cortex, where we measured these hypercolumns. You remember this from the pinwheel structures. What is a hypercolumn? We have the white and black bands here. That's the left eye white and the right eye is black. So these are the ocular dominance bands. And in these bands, we have small areas called a hypercolumn, in which we have this pinwheel structure with a singularity in the middle, and the spoke was a iso orientation. So all the cells with different orientations, and the biggest one was in the center, and you go out, you get smaller. So this is kind of a scale along the spoke. We saw that a nice experiment by the group of Fitzpatrick was done if you inject biocetin here in a vertical responsive area. So here we have receptive fields that detect vertical edges. If you wait for the biocetin to diffuse to other areas, you see where are the Bouton connections further away, and you wait for 1 or 2 weeks, you see that it has been diffused to other blue areas in a kind of an elliptic area. So the idea is that you say, okay, we have here all the blues connecting, all the reds connecting, and if blue, this should be rotated 90 degrees, by the way. If this blue guy says next door, hey, and he signals to me, I'm also vertical, and he tells, I'm also vertical, and this guy also, they all tell me I'm vertical, but we are also in the same line, and above me they also say I'm vertical. It's a voting mechanism, and that means if they all say, hey, we're on the same line, and we have the same orientation, we must be on the same contour. So that's contextual processing, not local processing. It has nothing to do with a local NJet of derivatives, or that they said I have my local texture, but I need very far away. I can go 10, 20, 30 pixels away. What are you telling me? So that contextual processing we used a lot. We made these orientation scores, so rotating filters, and for every rotation you get an output, so you make a space x, y, phi. And this space we call an orientation space or an orientation score, because this vertical axis is not really a space. It's not measures of x in meters, but it is in angles, so without a dimension. That's why we call it a score. The mathematics in this score is quite nice, because we found that if you take very special filters, we call them in the Fourier domain, these were these wedges in the oriented Fourier domain, and a wedge from a circular domain is like a piece of cake, so we call them cake filters. So if you take the inverse transform of a cake filter, you get beautiful filters that span up the whole space, and you don't lose any information. So you can have an invertible operation. And just like the Fourier transform, you can go to the orientation score and you can go backwards. So you do your processing and you go back. And the big advantage is that you have, at crossings, here you don't know what to do. What kind of filter do I need to enhance this? Now you have the possibility that in every pixel you can represent multiple orientations. So you have an extra dimension. Things get more complex, you need more space. That's why we have these hundreds of millions of filters in our V1. This is a very high-dimensional space. Multi-scale, multi-orientation, multi-disparity, multi-color, multi-time. So it is. We always say we should do data reduction or dimension reduction, make things smaller. It's stupid. Nature says you should just do the opposite. Explode. So an image that comes in goes to hundreds of millions of filters, so they make not just a single image, but they make from every image, they make a whole stack, a scale space stack, a multi-orientation stack. And then you can do a lot of contextual relations. So it is just the opposite. It's counterintuitive. Think about it. Seems crazy, but with our computer technology today, we have enough computing power to do the same. So these multiple orientations means actually I disentangle, I pull them apart, so I have an orientation here, and now I can have my cigar filters, my Perona-Malik, my coherence enhancing diffusion, whatever we discussed, you can do it now per level. And if you do this for optic disc detection, Erik Beckers, very good PhD student, now working at the mathematics department here, he was actually a cum laude also. I had 6 cum laudes in my career, so it's really nice to see how they wonderful work they did. He said, if I look at an optic image of the retina and I want to find this optic disc, sometimes really noisy, you can hardly see it, but I know that I use these arches of patterns, and I know that if I follow them back, they must, of course, originate from this thing. So even if I don't see it, I know it's there. That's contextual processing. If you have a map of the Netherlands and you see this is Oude Rijn, Klaverblad, or whatever, the traffic, you know, okay, Utrecht must be right there, because it is related. So you need contextual information. Well, that's exactly what he did. So he said, let's look at orientations. He looked at tangential orientations right here. So you got here the directions that are tangent, and here we have the directions that are radial. And with these 2 fields in his orientation score, he could very nicely measure optic disc in whatever image. If it was a very noisy laser scan image or a hardly well-illuminated RGB image, we found them with 100%. And that was because we used contextual-oriented information. It's a new kind of computer vision, not looking at these local things, but looking at the whole thing, the whole picture and the surrounding. And how do you do that? Well, you need techniques like this multi-orientation stuff. And how did we learn this? We looked at the brain and we saw, hey, we see these multi-orientation pinwheels. They talk to each other. Well, that's exactly what you see here. So that's why we were allowed to call this brain-inspired computing. It worked extremely well. So what's actually happening today, and I talked about Erik, he's now working in a group of Remco Duits. He also did his PhD with me, and he is awarded with a big European grant. He got 1.3 million euros, and Erik is now part of his team. And they do Lie group vision. So they study vision in all these different transformations that happen. So they make these multi-scale stacks, multi-orientation, and it's very nice mathematics, and it's very nice, really deeper understanding what happens. And you get a little bit, due to this course, the flavor of what's happening here. But the state of the art you can see by reading the papers of this LeaveVision group. They have a very nice website, leavevision.com or .net. And all the Mathematica software to process these images is freely available right there. So if you really want, in your PhD student or wherever later, you want to go further with this type of software, it's a very nice group to start with, read their papers and see what they do. Okay, I just said that this European Research Council grant. I have a second part. Now we go a little bit more in detail. What did we process? Let's go through the steps. The first step was image background normalization. And we know in deep learning, we always do a lot of background normalization. And why in the world is it necessary? Well, for two reasons. You may have inhomogeneous illumination, and you see that that's clear. That may be to all kinds of reasons. That may be due to the anatomy, due to the camera, or due to the lighting system. But the second is, our neural system is actually only looking at variations around the mean. So we always want to get rid of the mean. You want to do PCA around the mean. You have variations around the mean. So if we look at these patches and the self-organization, as we see, so the mean is always get rid of it. And that's exactly what happens here. Well, the first step we reached here is that we have, after this homogeneous, making it homogeneous. And how would you make this homogeneous? People do this already for decades. It's actually very easy. If you start from something very simple, engineering. Well, the most simple one is they say, well, all these background fluctuations have very low frequencies. So make the Fourier domain and kick away all the frequencies behind 1/10 of a hertz spatial frequency. It perfectly works. You smooth away all these things. You can also say, I take a local filter, and with that filter, let's say 100 by 100 images, I just calculate the mean. Sometimes I'm in the white area, sometimes I'm in the black area. You just subtract the mean, so everything is around 0, and you just convolve this big image with calculating the mean over your image. That's the same thing. So this is actually quite easy to do. This was a very clever technique found by Samaneh Abbasi, a PhD student of mine who did last year her PhD and is now working on the high-tech campus on a deep learning company that makes maps for self-driving cars. She looked at this multi-orientation stuff and she said, hey, if I have a filter that looks along a vessel, I get a very high output. But if I'm outside the vessel, I get a very low output. How can I enhance that? Well, very simple. Take the square. So if this output is 10, it becomes 100. If this output is 1/10, it becomes 100. But the difference is now 10 to the power 4. So that's much bigger. So you said, let's just look at every pixel, and in every pixel I scan the whole world, and I just take it to some power. Well, we call this a nonlinear orientation score transform. If you have then the very high output becomes really high, and the very low output becomes really low, because we have these cake filters, you can also do the inverse transform. So from your multi-orientation filtered images, you can go back. Just like the inverse Fourier transform, you go from frequencies to space again. Here we go from orientations to space again. It worked. You can do this in a very simple notebook yourself. You could even do it this afternoon. Calculate the filters, square them, and then you do the inverse transform. The inverse transform is very simple. Just add the whole stack of all these oriented filters, because they're all wedges in different orientations. And if you add them up, you have the whole space again. So you have to, it's an extremely simple inverse transform. So this works fast. And what happens here, you make the edges much more visible because they get bigger, and the surround, which was small, becomes not even smaller. So that's exactly what you want. The contrast, the surround is suppressed and the edges are there. But even the crossings, because we have this multi-orientation, it doesn't matter because they're in different fields. So that was nice. So we had a nice denoising, and you see that images from a laser scan are quite noisy. Suppose I take this image, I go back, this one, and suppose I zoom this guy out. You see the noise? It's quite amazing. But the laser scan has the advantage that there is very much contrast because it is absorbing in the hemoglobin, as I said, 531 nanometers. So the contrast is higher, but the resolution is lower, but that pays off. You also see very nice the difference here. This is an artery with reflections, and this is a vein. It's thicker and it's darker. If you have these multi-orientations, it's extremely simple. Look in every pixel to what happens when you make a rotation. And suppose you see that you have 3 maxima, of course you must be on a bifurcation. If you just see 2, you're on the vessel. If you see nothing, you're in the background. If you see 4, you have a crossing like those. So it's easy to make these landmarks. In a millisecond, you make them. And these landmarks, you make them, you can check them, what's the angle. People have 90 degrees, they're healthy. If it's outside of 90 degrees, so you measure a histogram, you have an early sign of retinal damage. So we made these kernels half kernels, and you let them just rotate around. And then you do these relatively straightforward calculations. This was a master student, Iris Okoloen. She's also working on the high-tech campus now. If you have all these markers, what we do is you let the people look at different fixation spots. You make, let's say, 9 fixation spots. You take 9 images, and you stitch them together. They're spherical images, so it's not really straightforward. You have to do some projective transformations of the images, but then you easily deform them with these landmarks. And with screening, you need to see a large area. If I see just, suppose I want to see some melanoma, and if I only see this small part of my hand, it doesn't make sense. You want to see the whole body and also want to see the whole retina. Today you have cameras that have laser scanning, and they can scan 160 to sometimes 180 degrees. It's very nice. It's called Optos. And Optos has some fantastic websites, nice to see how you scan the complete background of the retina. I'm currently talking to a company in Taiwan. They make all the optics for smartphones. And Optos is a big machine. I said, can you make the Optos in a 2 by 2 by 2 centimeter laser scanning device? There's multiple lasers, red, green, blue, and infrared, to put it on my smartphone and to have this at home. And they're looking into it. It may take several years to make it, but they said, I think we can do it. And then you have a very tiny scanning device. Because the problem is that you need to go through a 2 millimeter hole. That's the pupil. In hospitals, they give you eye drops, and then your eye dilates. It's easy, but it is invasive. A nurse needs to do it. It's expensive. You need to wait 10 minutes before you can do the measurement. After that, the patient has to wait several hours to recover, and he cannot drive a car home, and so on. So it is very, not handy. So if you have a non-mydriatic camera, as it's called, that camera is capable of taking through this 2 millimeter hole. And most cameras today are non-mydriatic. But that's a little bit special for the optics. Okay, we have the probability maps of the vessel. That's called soft segmentation. If you trace the whole them, you get the hard segmentation. And here we see a regular, healthy blood vessel pattern, more or less straight vessels. And this is diabetic retinopathy with a lot of curved vessels. This is so obvious that everyone can see there are curved vessels there. But if the curvature starts and you just don't know, it's very hard to see for humans. And we can, in particular, we cannot quantify this. You cannot give this a number. How much is this curved? We just don't know. And curvature is a pixel issue. So we take the center line of a vessel, and every point on the center line has a different curvature. It is the touching circle right there, and 1 over r of that touching osculating circle, that is the radius, that is the curvature. So straight has an infinite circle, that's curvature 0. But you have very high curvature, convexity, positive curvature, negative curvature is concave. So if you measure all these curvatures, and here we have measured these curvatures, and how did we do that? Was done by Erik Bekkers and Zhong Zhang. They fitted circles actually to every pixel of the center line, no, to every pixel in the image. And we fitted these circles in the orientation domain, and they became circles like this. It turns out to be a very stable way of measuring what is the radius of the circle that fits. And you have here all the measures color-coded. So you see that blue is 0, red is very high curvature, and yellow is very high curvature the other way around. And if you measure the straight values, then all curvature are 0. So the histogram of all these thousands of curvature measurements is a very narrow histogram around 0. If you now look at patients, you see much more positive and much more negative curvature. So the spread of this histogram is a measure for the degree of early damage to the retina. So here you see healthy and diabetic retinopathy, quite a big difference between the curvature, and this is then the standard deviation of the fitting Gaussian to this curvature. Simple measure, but it works quite effectively. So we have now a quantitative measure to measure this. We compare this with multiple cameras. So in Maastricht University, we had a good collaboration with the eye hospital. We sent several of our students there, and they had 6 different cameras. 15 students took all images from these 6 cameras, so we had a whole bunch of images. This is the same retina, and we took, of course, left eye and right eye, and 15 people. And then we compared all our software. Is the software vendor independent? Luckily it was, but you see there's quite some difference. This is a laser scan, so it's a black and white image. This is a low resolution, much cheaper, high volume screening laser scanning. This is an Indian company, Nidec and Canon and Topcon are Japanese companies, so quite some differences, but our software worked quite well. We did a lot of statistics on our images, and we used the Maastricht study. And the Maastricht study is the biggest diabetes study in the world. It cost 30 million euros. It's quite famous. They have 5,000 healthy and 5,000 diabetic patients, and they scan these patients with everything. So they have a separate building, and if you are allowed to this study, you will have a 1.5-day full examination with blood tests, urine tests, Cooper tests. Can you run ophthalmological scan? They make MRI scans. They do lifestyle interviews, lots of it. So they have an incredible database of all these metadata, so you know what is. And then they want to find out how is it related to each other, because there's not a single cause for diabetes. They want to see what's actually happening. You have 25 PhD students, and if you see, well, we have all these metadata and another metadata, how are they correlated? You make a matrix. All these cells are being researched, what is related. And we got access to the full ophthalmology data. That was really nice. So we could actually measure how much are these biomarkers that we measure, the number of microbleeds, the curvature, the fractal dimension, you name it, the branching angle, how much is it related to the status of diabetes? So the progression of diabetes. And we know exactly how much diabetes these patients had due to these metadata. So we were 88% right in. And of course, now we go to big data. We built a very nice workstation. Bedat, my postdoc, he wrote this. You have a patient selection item. You can make a whole pipeline of processing structures. And then this is for the research. You can see what are the intermediate steps. And to the right is a fully automatic report generator that reports what do we see quantitatively in your retina. And this is important for follow-up of these patients. They start to change their lifestyle. They start to take medicine. Sometimes they get treatment. You have laser treatment. If the leakage is too bad, you can just close these vessels. And then you can have longitudinal studies and see, are my parameters deteriorating or getting better, or are they stable? Of course, we used with deep learning neural networks. This we have discussed in extenso. And in this course, we started to understand this first level of interactions. And of course, the next step will be how can they be combined into more, this is called perceptual grouping. How can we put these edges into noses and so on? Tomorrow I will give you what steps are taken to make these next steps, and particularly what do we find in vision. Okay, we saw this multiple times. This was a deep residual network that Samane designed. It's a whole step of steps. And in the next hour, we're going to explore these networks in more detail. What does mean residual? Well, residual is you take the original, you take the whole processed pipeline, and you compare these two. So actually, again, looking at differences. How much did this small set of layers change my data? So I see what is the difference, what has been changed, and then you compare it with the original. That's called the residual neural network. They do very well, and they're very famous. And you can make steps of residual neural networks. You can concatenate them. So every block here is a residual neural network. We train them with the data sets that are now available on the internet. One data set, if you want to play and go around with huge number of data, I talked about the Kaggle challenge. Kaggle was this Californian company. You have 90,000 images from the retina, fully classified, right there. And in the end, I'll show you some examples. It's only 180 gigabytes. You download it, and you have a lot of data to play with. So that's the recommendation. It's fantastic, nice material to have a look. And if you want to find microaneurysms, they're right there. They're specified in special groups. There is a comma-separated value spreadsheet with it. It's very easy playing with it. And these other challenges, we saw them before. There are now websites with all this website biomedical imaging challenges. And all these big data sets for tumor detection in the liver, tumor detection for whatever disease, are right there. But the biggest one is this retina. But of course, if you process 90,000 images and they're all 12 megapixels, you need some hardware. It's not easily done on your laptop. It's just too big. But you can rent hardware. You can just go to Baidu, to Google, to AliCloud, wherever you can easily find it. Samane worked on the detection of exudates. And this is a very nice breakthrough, because if you find the exudates here, and the neural network did a pixel-wise classification, so we could see from a pixel, okay, this is a two-class decision-making. It is either an exudate or it is a normal pixel. So for every pixel, that decision was taken, and now you see nicely. But to validate how this works, what you actually need to ask the doctor is circumline all these small areas and check if the ground truth is what my computer says. So it is more or less the same. Well, in this case, we trained the system not with a system like that the doctor gave us this ground truth. We only had to say to the system, somewhere is something. So there's an exudate somewhere, but we don't have to locate where. That's much easier for the doctor. So the doctor could very easily take hundreds of these images and say, okay, this is a clean image, and this is an image, there is something. So we could train it with image-based pathology, and we got back pixel-based pathology. Well, that was a major step. That saves a lot of time in training. And it was done with these feedback loop neural nets that take, again, the difference. So it's fully automatic, and it says pixel of image-based in and pixel-based out. That's a big step if you want. I mean, then you don't need to burden the doctors with draw all this. And of course, we compared it with what the doctors, they did not sign, of course, every individual thing, but they draw with big areas. But you see the numbers, 99, 97% right. This is super. This is really, really good. So this means we have a very powerful tool, and this tool is now going into Chinese healthcare. And I'm very happy that this happens, that we really could build. We did a research phase here at TUE. We wrote all the, let's say, developments, and now it goes into practice. Still a lot to do and a lot to build up there. I go help them, but not lead the whole thing. well, this is what Erik Beckers talked about. How can we do this contextual processing and what types of mathematics do we need? And Erik gave this beautiful overview of if you stand in an environment with lots of structure, you say, I have a connection here and I have a road here. How in the world are they connected? I have to go from this place to that place. And he said, well, it should be restricted. It should not be anywhere, any orientation, but it should be not Riemannian all over the space. We call it Riemannian space. We are here in Riemannian space, but in sub-Riemannian space. So we said, take the analogy that I'm sitting in a car. I'm limited. I can only move forward or backward. And I can take my steering wheel, so I can move a little bit to the left, to the right, but I cannot move sideways. Well, that's called sub-Riemannian. That turns out to be super effective. So if you do sub-Riemannian connections, you find the optimal connections that you also logically would say, well, how much is that connected? You never go sideways or so, but you say, I'm sitting in a car and I drive to that, which is the shortest road I drive to there. Well, these shortest roads are called geodesics. In mathematics, you can easily find these geodesics, and they turn out exactly the connecting lines. So if you have missing blood vessels, they're interrupted or noisy or whatever. With this sub-Riemannian connectivity, we could easily close them and find the whole blood vessel. We participated in this Kaggle challenge. I showed this before. We only worked 1 month on it. We discovered this too late. Of course, we wanted the $100,000 rewards, but we were only number 17. But we were quite happy with number 17. That was not too bad among 661 teams. How did we validate the whole thing? That was done in the biggest hospital in Shenyang, 3,000-bed hospital. And it's called Shenzhen Hospital. They have a special diabetes department, and we made a special room in this department. That was quite nice. We knew the head of the department. So we set up a retina check room, put cameras in there, and every patient, they had 30 new patients every day. We took the pictures. We connected to the hospital information system. We could load all the metadata, the blood samples, etc. It was all in Chinese. Nurses didn't speak any English. It was not trivial at all. With my Chinese students, we could handle this, but it was a fascinating time. I lived there actually for a long time. I was about 1/4 of my time in Shenyang. This project got bigger and bigger. We had more and more hospitals. I had about 15 Chinese students over there. I gave lectures. You have to talk to the doctors, and most of the doctors are trained in the West, so the doctors speak English, but everybody else does not. And Shenyang is in the north of China, so it's a little bit of outside of the Beijing, Shenzhen, Shanghai area, where it is very international. Here it is not international. I sometimes felt that I was the only international guy in this city. You see my Chinese students. This was a biomedical engineering student who did an externship. He was my master student in Shenyang and fell in love with a Chinese girl and decided to stay there. So he became a lecturer in the school, was a good friend of mine, and he speaks Chinese fluently. Very nice guy. This is the diabetes study in Maastricht. It's a 10-year study. As I said, these 5,000 diabetes patients and 5,000 normals, they track. They do over a long time these measurements, so they can also see what is the longitudinal effect. And everything is done. And Tos Berenschot is my colleague. He's a clinical physicist, and I'm also a clinical physicist. I was president of the Society of Clinical Physicists, and he was the secretary some years ago. So we had many, many meetings, and after some years then started a new collaboration from Eindhoven with Maastricht. It was a very natural thing. And tonight I go talk to his group of ophthalmologists about the recent results in our project. This is the room we built in this hospital in China. You see some patients, and it was continuously going on. I paid for the operator, and we have different cameras. This is the laser scanning. I put some pictures on the wall with tulips, so you see this is a Chinese-Dutch collaboration. Patients liked it. And we did more than 3,000 patients. This was already in, actually, this should be 2018. I should change that. We took images from left and the right, disc and the fovea, and this is the connection to hospital information system. All patients have an ID card. We made a reader, so you scan the ID card, and then you know the whole, let's say, early demographic data. You know his address, his age, how he's insured, whatever. So you don't have to type it in. And if you go to high volumes, that's necessary. So you see the setting up and how it all worked. My students had workspaces here. This was really nice over all these years. Every student had to, every patient had to sign an agreement, because this was research, that it was okay to take a picture from there. So we had lots of these texts, and you see Xi Jinping, the operator. And we did data acquisition in these vision stores. You see me here in one of these stores. We had DRS cameras, that's an Italian company. They're fully automatic. You sit down as a patient or as a person, the camera automatically finds the pupil, automatically does autofocus, automatically takes the picture, so the operator only has to press the button start, and then the whole thing is taken. And this goes the whole day. So we had thousands of these images. And we had a WeChat app, of course we still have. The patient can see the image that is taken from him. He sees the first report that is done from the analysis. And of course, we now go to a commercial thing. You can get an eye check, and you pay for it. And you can get the eye check in a regular way. So you pay actually a relatively small amount, but it goes in high volumes. A percentage of this amount is for the camera owner. Another percentage is for the network distributor and the eCloud service. Another percentage is for retina check, deep learning doctor. So that's actually the whole thing. And that's how we are going to make the commercial thing. We got a lot of funding. It was really nice. I had to, of course, write proposals, what to do. I got funding from the European Diabetes Foundation. There was a start funding, 90,000 euros. We could buy cameras. I had a big funding from the Dutch government. I got 660,000 from the Chinese government. I got 500,000 from the European Union. And with that, I had a small team of PhD students that I could pay for 4 years and do the research. And we had a lot of publications. If you want to read them, check this, retinacheck.org, and you see all of them. And it goes about orientation scores, vessel detection, enhancement, you name it, validation study. It's quite nice. We set up a Sino-Uran Vision and Brain Institute together with Professor Ge. This is the governor from the province of Liaoning. And all these things were very nice let's say as a project, it was really nice. And the nice thing is, in China, you need the support of the top. Only then it works. And we got the support of the top. It was really nice. We had Professor Ge, who is a very, very big shot. Professor Kang, who was the director of Newsoft software thing. Both of them became very good colleagues and friends, and that was a major step into going into Chinese healthcare. This, by the way, is Professor Kang. So I had some really fascinating years here, now retired, but very happy to see that the things go on and land where it has to land in Chinese healthcare. And Professor Ge has received a major grant to, let's say, kick up the healthcare for eyes in Northeast China, so has a major investment fund, and that's what he's now using. So look for a job in Northeastern China, have a look at this development. Okay, and in this brain study we do a lot more. One of the fascinating things is Professor Haki. He is, like me, also appointed in this Northeastern University, Dongbei Dachue. He is studying microbleeds, like we do in the retina. He's doing it in the brain. And it's, of course, fascinating to see if it is correlated. I also have some publications with Thomas, what's his name? I'll mention it in a minute, PhD student in Nijmegen, who's doing the same microbleeds. And if you see the movie, it's pretty clear what happens, and this is actually what diabetes does with your blood vessels all over the place. You think it's only in your retina, but it is all over the place, and this happens in your brain. So this leads to all kinds of other things, of course. So people are now studying relations with this, with the development of early neurodegenerative disorders like Alzheimer, all kinds of depression, dementias. And what we like to do is, of course, if you take a 500 euro MRI scan and you compare it with a 1 cent scan of the fundus and it gives the same information, what do you take? Especially when you screen the whole population, you want to go to this fundus. So there's a very interesting role for this retina to see how informative is it. And we also looked at optic tract visualization, but we saw these images before. By the way, a company is Qmenta. 3 of my PhD students work in this company now. It's in Barcelona. They sell these tracking of connections in the brain commercially. So for 1,000 euros, you can get your whole patient tracked. You submit your 3D data set. And they have a very nice company, Qmenta, that as a startup, they do very well. I think it's already 25 people. Okay, I gave lectures there, was on television, and we had a lot of collaboration. This is the biggest brain institute in China. It's called Brainatome. Professor Chanse Jiang is the chairman, and he invited me several times, I know him very well, to be speaker in this meeting. Here we see them together. And we tried to get more money. This was from the Bill and Melinda Gates Foundation. It didn't work. We had a whole program, Vision for Vision. But here we have the leaders in ophthalmology of the world. It's quite nice. This person is the head of the International Ophthalmology Council. So they make the guidelines how to check all these eye images. Anyway, and I was invited at the dinner that the king was giving with the Chinese president. And during this dinner, I was one of the 50 people who could sit at this fantastic event, and pretty close to the Chinese president. It was very special. So I had a nice role in this whole thing. Okay, so there are a couple of challenges, still what to do. This deep learning has to explode right now. We have all the things going on, so this company is now focusing on setting up a lot of deep learning. And in the exam task, I have some examples where I want you to do deep learning on these images as well. So, easy to conclude. You saw all these images. We had a fantastic combination of what do we learn from the brain. It finally goes to practice, and we are part of this blindness of prevention program that by 2020 we want a lot of preventable blindness out of this world. But I want to thank most of the Retina team members. So this concludes my Retina Check presentation. So let's make a small break right here. And then I completely go to a different topic. We go dissect trained neural networks. We take them from the internet and we go look what happens inside. What do they do? So that's a more practical area. But this was an hour about how does it work in practice. Yes, it works. Still a lot of work to do. Let's have a coffee break, 10 minutes, and be back.